Hello everybody, welcome to the next video of the subject fluid mechanics, and in this video or in this series of videos you're going to study about buoyancy and flotation. So before we start with the concepts of buoyancy and flotation, I would like to mention that few students out there tend to believe that light objects always float on water whereas heavy objects sink into it. Well, if this conception or if this concept was to be true, then you all should also be able to reason out why does a heavy ship which is made up of metals and other heavy equipments, it floats on water, whereas a tiny piece of metal such as an iron ball, it sinks into it. Well, to answer questions like these now, you'll need to understand the concept of buoyancy and flotation. So at the end of this video, you will be very confidently able to answer the above asked question, and at the end of these series of videos which we will be covering, which will consist of, the first video will be consisting of what is the buoyant force and what is the magnitude of buoyant force. In the next set of videos, we will be discussing about the stability of submerged bodies, and then we are going to study about flotation, that is the study of floating bodies. And then we are going to study about the meta center, and we are also going to see how with the help of meta center we can define whether the floating body will be in stable equilibrium, unstable equilibrium, or in neutral equilibrium. So let's just start our concepts about buoyancy and flotation. And at the end of this series of videos, you will not only be able to answer the above asked question, but along with that you will also be able to answer questions which are related to the topic buoyancy and flotation, and the questions which are asked in your competitive exams, that is questions related to buoyancy and flotation which are asked in your competitive exams. So let's just get started with the concepts of buoyancy and flotation now. So talking about buoyancy, or what exactly is buoyant force, we can understand this with the help of a practical example. That is, you all must have been to a swimming pool, and you all must have observed that as soon as you'll get into the pool, you'll tend to feel a bit lighter. As you can see from this figure as well, there is a boy who is inside the swimming pool, and as soon as he gets into the swimming pool, he tends to feel lighter. Now this can be experimentally verified as well as to why you all feel lighter inside the swimming pool. Now for this you'll need to conduct an experiment, and in this experiment, when the object is weighed outside water with the help of a weighing scale, let's say you'll get some weight, let's say that you'll get 40 kgs, but the same object when it is weighed out inside water, when it is submerged inside water, and when you weigh that object, now you get a slight decrease in weight. That is, initially when the object was 40 kgs outside water, the same object is now weighing 30 kgs when it is submerged in water. Now what might be the possible reason for the reduction in the weight of the object? Now let us have a discussion on it. Now when you will take the object which is outside water, or when you will submerge this object inside water, both the objects are the same. That is, the mass of this object and the mass of this object are the same, because the material and the dimensions are same, both the objects. But what happens is, whenever you immerse any object inside water, or in general whenever you immerse any object inside fluids which consists of both liquids and gases, so whenever you immerse an object inside fluids, you will observe that fluids have a natural tendency to exert a vertical upward pressure on the object. Fluids have a natural tendency to exert a vertical upward force on the objects, and due to this there is a force that comes into existence when the object is immersed inside water, and that is nothing but the buoyant force. So buoyant force is nothing but a vertical upward force which is acting on the object when the object is immersed inside fluids. So in this case our fluid is water. So now we shall see that two forces are acting on this body now. One force is due to its self weight. One is due to its self weight, which can be stated, we can consider it as W, and it is 40 kgs. Okay, because we had taken the weight here as 40 kgs. Now, but still the weighing balance is showing us 30 kgs, and this reduction in weight is due to the buoyant force, because it is exerting a vertical upward pressure against the self weight W. Vertical upward force, you can say. It is exerting a vertical upward force on the object, and due to this buoyant force, which we can name it as FB, there is a slight reduction in weight of the object which is immersed in water. Now we know the magnitude of W, that is 40 kgs. But what will be the magnitude of buoyant force now? Let us calculate the magnitude of buoyant force. In order to calculate the magnitude of buoyant force, we need to consider an equation which is given by Archimedes. Archimedes is a scientist who discovered the phenomenon of buoyancy. So what Archimedes gave, so according to the equation which is given by Archimedes, the buoyant force is equal to the weight of displaced fluid. According to Archimedes, or according to the Archimedes principle, the buoyant force is equal to the weight of the displaced fluid. Now we understand that the buoyant force, or the magnitude of buoyant force, it is some weight, it is a weight of some displaced fluid. We can say it is a weight of some displaced fluid. Now let us see what is this displaced fluid. Now whenever this object is outside water, let's say that this beaker or this container is fully filled with water here. Okay, it is fully filled with water. Let us assume that it is fully filled with water. But as soon as this object is immersed inside water, some quantity of water is going to get spilled out. Some quantity of water, as soon as this object is immersed inside water, some quantity of water is going to get spilled out in order to make space for this object, or in order to accommodate this object. Now whatever water is getting spilled out, or whatever water is getting expelled out, that is nothing but your displaced fluid. So this was the case when the beaker was fully filled with water. Now let's say that this beaker was not fully filled with water, but it was up to this level now, or let's take the original level. That is, this water was up to this level only, and when you immerse this object, this level was slightly raised. When you immerse the object, the level was slightly raised. Now this volume of water between the original surface and the raised surface, this will be your displaced fluid. Now this is the second case. Now third case is, what happens, the water level also raises from this level and then it starts spilling out. In this case, whatever level of water, then the displaced fluid would be the level of water from here to here, that is the level rise plus the spilled water will give us the displaced fluid. So the displaced fluid can either be the spilled out water when the beaker is full, or when the beaker is not full, the rise in level will give us the displaced fluid, or when there is a rise in level and plus the expulsion of water, that time we have to take the displaced volume of displaced water as the rise in level plus the displaced fluid. So now we know what is the displaced fluid. Now the next question is, so buoyant force is equal to weight of displaced fluid. We know what is the displaced fluid now. If we calculate the weight of this displaced fluid, we easily get the buoyant force. Now the next question is, what will be the volume of displaced fluid? Because weight can be calculated, weight of the displaced fluid can be calculated only when we know the volume of the displaced fluid. So let's see what will be the volume of displaced fluid now. So talking about the volume of displaced fluid now, whenever this object is immersed inside water, this water or this beaker has to make, or by removing some quantity of water from the beaker, so that this object can be accommodated into it. Now in order to make this much space inside the beaker for this object, the same volume of water has to be removed out in order to make space for this object. So we can say that the volume of water that is being displaced out is equal to the volume of the object, because the same volume of object has to be accommodated here, and in order to accommodate this volume of object, this much volume of water has to be expelled out. That is, let's say this much volume of water has to be expelled out in order to accommodate this object. Now the weight of this volume of water will give us the buoyant force. So what had we discussed? Whenever an object, let me just repeat all the concepts to you once again. That is, whenever an object is immersed inside water, there is an upward vertical force which is acting on the object, and that vertical force is called as the buoyant force, and the magnitude of this buoyant force is equal to the weight of the displaced fluid. Okay, so it is equal to the weight of the displaced fluid. So in order to calculate the weight of the displaced fluid, we need to know the volume of the displaced fluid. Displaced fluid is nothing but the rise in level or the expelled out water. So the volume of the displaced fluid will be equal to the volume of the body which is immersed in water. So we get the magnitude of the buoyant force now. So this was just a theoretical discussion of what exactly is the buoyant force. Now let us derive the mathematical expression for buoyant force, and let us cross verify whether the buoyant force is actually equal to the weight of the displaced fluid. So let us have the derivation now. That is, let us first write down the statement for buoyancy or buoyant force. We can say buoyancy. So we can write as whenever an object is immersed, or we can say partially immersed in liquids, or we can say fluids, the hydrostatic lift due to, first write down the statement and then I'll explain it to you all what is the meaning of the statement. Whenever an object is immersed or partially immersed in fluids, the hydrostatic lift due to the net component of, due to the net vertical component of, net vertical component of hydrostatic, net vertical component of hydrostatic pressure force, hydrostatic pressure force is called as buoyant force, is called as buoyant force, and the phenomenon is called as buoyancy, is called as buoyancy. So let us understand this statement with the help of a figure now. So this is your surface of water. Let's draw it at the side, or let's do it on the next page. This is your surface of water, and let us immerse an object into it now. Let us take this cylinder. So this cylinder now is immersed inside water. This is your water. So let us show some water here. So it is immersed in water now. So it is fully immersed in water. So let us say that the pressure at, let's say this is point M and this is your point N, and let's say the pressure at point M is equal to P1, and let's take another color. Let's say the pressure at point M is P1 and the pressure at point N is P2. Okay, and the point M is at a distance of h1 from this free surface, and point N is at a distance of h2 from the free surface. It is at a distance of, this is at a distance of h2, and point M is at a distance of h1 from the free surface. The cross-sectional area of the surface, both this, the top surface and bottom surface, for both the cross-sectional area is, you can say, for both the cross-sectional area is equal to A. Now due to this pressure force, or due to this pressure P1, we get a vertical upward force, we get a vertical upward force here, or we can say that due to this pressure P1 we get a force here, that is nothing but F1, and F1 will be equal to force is nothing but pressure into area. So F1 will be equal to P1 into A, and due to this, at this surface, due to P2, we get another force which we can write it as F2, that is equal to P2 into A, because force is equal to pressure into area. Now what does our statement say? What does the statement of buoyancy say? Whenever an object is immersed or partially immersed in fluids, the hydrostatic lift, that is, you need to understand what is this hydrostatic lift, due to the net vertical component of hydrostatic pressure force. What does this say is, due to these two forces, that is due to this F1 and F2, we get a net upward lift on this body due to the forces F1 and F2, or we can say due to the resultant of F1 and F2, we get a upward lift, we get a vertical upward lift, which is nothing but the buoyant force. This buoyant force is equal to the resultant of F1 and F2. As we can see here, the hydrostatic lift due to the net vertical components of hydrostatic pressure force. F1 and F2 are nothing but the hydrostatic pressure forces, that is the forces due to the pressures at the respective surfaces. We have taken a lecture, we have studied in detail about pressures in our previous videos, so you all can watch that as well to understand in detail what exactly is pressure and how do we measure pressure. So due to P1 we get a force F1, and due to P2 we get a force F2. Now the net resultant of these two forces F1 and F2 will give us the buoyant force. So let us take summation of the forces now, that is summation F is equal to 0. F is equal to 0. So the net resultant of F1 and F2 will give us the buoyant force. So let us write FB is equal to, so it will be F2 minus F1. Since F2 will be greater than F1, we will write F2, it is equal to F2 minus F1. So what is F1 and F2 now? Let us understand what is F1 and F2. Now let us take the hydrostatic pressure force at surface F, surface M. Okay, so let us write down hydrostatic pressure, or we can say hydrostatic pressure only at surface M. Okay, so that is equal to P1. P1 is equal to rho g H1. H1 is the height from the free surface. We have studied it in our previous units, that pressure is equal to rho g h. Now what is hydrostatic pressure force? Hydrostatic pressure at surface n. So we will have P2 is equal to rho g h2. Also we can further write it as FB is equal to, what is F1? F1 is equal to P1A1 is equal to P1A1 minus, or it is F2, right? So it will be P2A minus P1A. So this is your equation 1. We can name this as equation 2 and this as equation 3. So we will have from 1 substituting 2 and 3 in 1, what we get is FB. Let us take it on the next page. Now we will write one step here. FB is equal to, will be equal to rho g h2 minus rho g h1. Let us take rho g common, that is FB, the buoyant force, is equal to rho g into bracket h2 minus h1, be equal to rho g h2 minus h1. So let us observe what is h2 minus h1 here, and we will have area which is common outside. So let us rewrite this sentence again. So FB is equal to rho g h2 into A minus rho g h1 into A. So it will be into A here. So you all will observe that. So we need to find out what is h2 minus h1 now. So when we see from the figure, h2 minus h1 will give you all the length of the body, or the, in this case, length of the cylinder. So h2 minus h1 is nothing but the length of the body. So we can write it as FB is equal to rho g into length of the body into area, and length into area is nothing but volume. So we can write it as rho g into volume. So this is your expression for buoyant force. Let us put it in a box. So is equal to rho g v. But according to Archimedes' principle, what we had got is, he stated that buoyant force is equal to rho g v. He had stated that buoyant force is equal to weight of displaced fluid. So let us see if rho g v will be equal to the weight of the displaced fluid. So let us have a discussion at the side here. J, that is here at the side. So we know that density, let us understand what is density. Density is nothing but mass by volume, or mass density is equal to mass by volume. You need to know that mass is nothing but weight upon acceleration due to gravity. So density is equal to divided by g, and this volume is as it is. So W is equal to rho g v. So from here as well we are getting W is equal to rho g v, and W is nothing but the weight of the displaced fluid. Here we can write for displaced fluid, okay, rho is nothing but the density of the displaced fluid. I'll write it here, that is rho is equal to, okay, we can write it as directly rho here, and we can write it down here, rho is equal to density of displaced fluid. Okay, so I hope the concept of buoyancy and the magnitude of buoyancy, whatever we had calculated, is clear to you all. Let us now try to answer the original question, that is, why does a heavy ship float on water, whereas a tiny piece of metal such as an iron ball, it floats on water. Now you all should be able to observe that buoyant force is equal to the weight of displaced fluid. And when will the buoyant force, that is, when will the upward vertical force, that is buoyant force, will be more? It will be more when the weight of the displaced fluid is more. So when will be the weight of displaced fluid be more? When the volume of displaced fluid is more. And we can get here, we can see that when we consider the case of a ship, this much volume of water, can say this much volume of water is being displaced out and it is being replaced by this ship. So you all can see that this is a huge amount of volume now. This is a huge amount of volume that is being displaced. So greater the volume of displaced fluid, more will be the weight of the displaced fluid, and more the weight of the displaced fluid, more will be the buoyant force. That is, on the ship, larger magnitude of buoyant force is acting, and when the upward force which is acting on the ship is more, it tends to keep the ship in floating condition. So more volume is being displaced, that is why more will be the buoyant force that is acting on the ship, and therefore more will be the its tendency to float on the surface of water. Whereas if you consider the case of a small metallic ball, what happens is the volume of this ball is very small, so only little amount of water is being displaced out. And since only little amount of water is being displaced out, the magnitude of buoyant force is going to be very small, that is, the vertical upward force is very small, and since the force is very small, it does not tend to keep the ball in floating condition, and that is why it sinks into the water. So I hope you all have understood the concept and you all have understood the answer as well now. So let us move to the next concept, that is stability of submerged bodies.